Hello everybody, and welcome to our webinar on IoT device testing with the LTE LabKit. I'm glad you could join us. I'm here also with Rob Guldutza from Nuand, the company that makes the actual SDR radio that we use. This seminar will take about an hour, and we'll take questions via chat and then answer them at the end. So for starters, what are we going to learn here? We're going to talk about production line testing for IoT products. We're going to talk about testing tools with the LabKit that are useful in IoT product development. And then at the end, we're going to talk about IoT test equipment and test fixtures that you would use to implement some of these tests. So we're actually going to start by talking about product development testing. And in product development testing, the sort of big question is, how does my product behave under different network conditions? Oh, I just got informed that my video feed was on the wrong thing. Okay. Thanks. This is the first time we've done a webinar, so bear with us here. So I'll back up one slide since you didn't see it. What are we going to cover? We're going to cover production line testing for IoT products. We're going to cover development testing for IoT products. And then we're going to talk about, at the end, after we talked about all the various types of tests, we're going to talk about test equipment and test fixtures. So we're going to actually first talk about product development testing because I suspect that that's probably a bigger interest area for the people who've signed up for this today. And under product development testing, again, the big question is, how does my product behave under different network conditions? And there are two aspects to this. One is application testing, the testing of your software and how it behaves, and the other is hardware testing. How does your actual IoT device hardware behave in testing? And we're going to talk about the different tools that are available through the LabKit to support this testing and some of the tests that you might want to do. So one of the first and really powerful tools that we have is protocol tracing with Wireshark. And this answers the question of what's really happening on the radio interface. So if you have a device that might be not connecting to the network as quickly or as reliably as you expect, or if you have a device whose only IP interface is through your mobile network, through your mobile networking connection, Wireshark gives you some visibility in what's going on there. And to do this, we're going to switch over to a Wireshark display. And this is a Wireshark display for a device that's connected right now. This is a trace from the MAC layer, and what it shows is the initial setup operation. The initial setup operation for a mobile device connecting to the LTE network. So you see the setup request, setup complete and service request, the security mode operations, connection reconfiguration, which is where the data bearers get it set up. And then we see all these other packets, these data packets that are actually carrying user traffic payload uplink and downlink. And with Wireshark, you can look into these packets and actually see the traffic at the IP level, depending on what kind of encryption is going on. But you get visibility into these packets, and you can see exactly what the application is doing on the IP interface. From the IP layer all the way down to the LTE MAC layer. And the way to set this up is fairly simple. You log into the device, you access it through a telnet interface. I'll back up so you can actually see me do this. Connect to the eNodeB over the telnet interface, and we can look at the status. We see that MAC capture is active. Okay. Another thing you can do with the LabKit is you can simulate different network configurations. And we have customers who do this. Two different cases where customers do this. One, we have a mobile operator customer who does this for roaming testing to see how their devices are going to behave in networks that have inconsistent configurations. And the other is we have a customer, we have multiple customers who are checking how devices respond to public service messages, like in the United States, presidential alerts, or in Japan, the earthquake tsunami warning system. These systems go by different names, but they all do pretty much the same thing and work in pretty much the same way in LTE. So actually doing this by hand takes a few minutes to set up, and it might be kind of tedious to go through in the webinar live, but I'll give you some examples on the whiteboard real quick. So let's switch the video. Hi. So for this type of testing, what we're going to do, sorry, get a pen. In the configuration directory of the LabKit eNodeB, there is a set of XML files. And these XML files get translated in real time into what are called SIBs, or System Information Blocks. And these System Information Blocks describe to all the UEs in the service area, all the devices in the service area, how the cell is configured and what services it offers. And you can come in and edit these by hand, and I'll show examples of a few of them in just a moment. So things that we have seen customers do with SIBs that they found useful. One is to do inconsistent SIBs, which means SIBs that advertise services that are different from what the cell actually does. So the cell will basically tell the mobile device, hey, this is the service that I offer, and this is what I'm going to, this is how I'm going to treat you. But then when the device connects, it behaves differently than what the device would have expected. And this is a useful type of test for interoperability testing and also for security testing. Then another thing that we see customers doing is, again, the public service messages. And in LTE, public service messages are carried in SIBs. And if you click on the title of this slide, it'll take you to it's a web link that'll take you to an application note where we show a specific example of this with SIB 12, which is the earthquake tsunami warning system, which is the emergency public service announcement system in Japan. But like I said, the others all over the world work pretty much the same way and are configured pretty much the same way, with different SIBs, 11, 12, and 13. So cut over back to the login session and show you examples of the SIBs. So this is an example of SIB 7. SIB 7 controls mobility information related to GSM networks. So if an eNodeB supports some sort of mobility with a GSM network in the same operator or with a related operator, SIB 7 describes how to find that GSM network. Tells the eNodeB how to look for the neighboring GSM network. And when you look at the SIBs, again, this is covered in the application note. You'll see in some places you'll see symbols starting with a $sign, and these are values that are substituted from the eNodeB configuration. And then in other cases, you can just put values in directly. So you have the option when you do this either to put values in, real values from the configuration, or you can just go in and put whatever values you want, regardless of the eNodeB configuration. And we show another example here. This is SIB 6. SIB 6 controls mobility information related to UMTS 3G networks, similar to SIB 2, to the GSM SIB I showed you a minute ago. But again, if you go look at the application note, you'll see a much more sophisticated example with SIB 12 sending out a public service emergency announcement message. Okay. The next things we're going to talk about would be tests that involve multiple LabKits. And later, toward the end, we're going to talk about core networks and EPCs and the different test equipment and test fixtures. But just at this point, accept that if you have a hosted core or a MiniCore, we'll define those a bit later, but whatever core network you're using, you can attach multiple lab kits to them and operate them in any combination of LTE or GSM. And they all become part of the same network and they use the same set of SIMs. So I'm going to talk why would you do this? And we'll give some examples of this again back at the whiteboard. So in the mobility case, we have a common core network, common EPC of all packet core that is, let's say you have two lab kits connected to it. And you have the device under test that is potentially in communication with both lab kits. So by altering the transmit power of the two lab kits, you can simulate the movement of the device under test from the coverage area of one cell into the coverage area of the other. So if I lower the power on this one and raise the power on this one, that's like the device under test moving, physically moving from one cell to another. And by doing this, you can induce mobility and handover behaviors, and then see how your device under test is going to behave. Because in the simple example, in the simple obvious case, these are both just normal LTE cells that are attached to the same network, but they don't have to be. So, for example, one could be LTE and one could be GSM GPRS. And what this does is it simulates what happens when your device under test moves from an LTE network into an area that doesn't have LTE coverage and has to fall back to a 2G network. How does your application behave? How does your product deal with that? Does it deal with that gracefully? Another thing you can simulate is it simply goes out of coverage and loses coverage, period. Another thing you can simulate is if you have a MiniCore, you can actually simulate roaming, where you've gone from the coverage area of one operator into the coverage area of another, and you've actually performed mobility across operators. And does your application deal with that gracefully? So these are the types of tests that you can do with two lab kits. Again, mobility across operators, mobility across technology types, and as your device under test moves back and forth, how does your application respond to that, and do things still work? Okay. The next thing that you can do with a lab kit is you can do hardware testing and measuring device emissions. So if you have a device that's going to be installed in a situation where emission control is very important, say on an aircraft, then you will need to do compliance testing to be sure that the emissions that come from your device aren't going to cause what they call electromagnetic compatibility problems in the place where it's going to be installed. And the setup for that, we have this set up right now. The setup for that is back to the whiteboard. The setup for that is something like this. Again, you have the lab kit, usually in a wired connection to the device under test, and Rob will come in Rob will come in a little later in this webinar and talk about different ways to perform these physical connections. But conceptually, um, and then conceptually, you have the LabKit, you have the device under test, and then looking at the connection between them, you have a spectrum analyzer. And you might route these signals with different combinations of splitters and circulators. Again, Rob will talk some about this later in the webinar, but conceptually, you can think the spectrum analyzer is snooping on the radio communications between the LabKit and the device under test. And you're doing this so you can see what's actually coming out of the device under test, what radio emissions are coming from the device. And the LabKit has some special features to help you support this type of thing. One is it allows you direct control of the modulation on the uplink, and the other is it allows direct control of the transmitted power from your device. So you have direct control over power, you have direct control over the modulation type, and under those conditions you can drive the device under test into different extreme cases to see what's actually coming out of it. And while we've been presenting, we have a Huawei B310 Flybox that's connected to a LabKit here in the office, and we've just been measuring what comes out of it. So I'll switch over to the cameras, go over and show you the display. So here's our system. Here we have the spectrum analyzer showing the emissions from the device under test during the time that we've been, since the webinar started about 20 minutes ago. This is a band 3 device. You can see center operating at 1.74 gigahertz. The actual device is this Huawei, what's called a Huawei B310 Flybox, which is a sort of hotspot. And you can see the test fixture that we're using to connect it, and we'll draw that on the board in a little more detail. And Rob will talk about this type of thing in a few minutes. So give a little more detail on the test fixture that we use for this in this particular case. We have the LabKit. It has a transmit and receive. We have a pair of 30 dB attenuators and a splitter and another splitter and the device under test and the spectrum analyzer. So that's the test fixture that we're running right now. You can see that a little better. Okay. So now we're going to talk some about production line testing. Get the slides back up. Okay. Production line testing. Now, production line testing is different from production line testing is very different from development testing. Production line testing is really about making sure that a device has been assembled and configured correctly before you ship it. And this is the type of thing that goes on in the factory at the end of the assembly line. The typical production line system, testing system, is going to be automated. And here we have, working from the left, your IoT platform, which is probably cloud-based, whatever IoT platform your application works with, the EPC, your LabKit, eNodeB, and the mobile IoT device, the device under test. And then coordinating all this and sort of closing the testing loop, we have the test control system, and then the operator. And these systems are they're designed, even though they may do very sophisticated tests, they're designed to be very simple to operate. Usually the operator just connects the device, initiates the test, and then at the end of the test gets a simple go, no go kind of result. And these different communication interfaces between the IoT platform and the test control system, it's probably some sort of it's probably some sort of web-based API. Between the mobile IoT device and the test control system, it's probably a serial port connection. That seems to be most common. And then between the test control system and the LabKit, it's going to be an IP connection. You actually have two options there. One is to send and receive strings over a telnet interface using the same interface that you see me using by hand in parts of this webinar, and the other is through a JSON interface, which is a little more sophisticated, but it's pretty much the same functionality. So what are the types of testing that you're going to do here? The testing really falls into two parts. There's end-to-end testing and there's RF testing. Now, because the LabKit is it gives you a true full-blown LTE network, you can do the end-to-end testing with your standard production IoT platform and with your standard production SIMs. And if you have a MiniCore, this would include even doing testing with eSIMs. And we're not going to really, end-to-end testing is actually something that happens. When we go back to the previous slide, end-to-end testing is something that happens between the mobile IoT platform and the device under test. The LabKit itself doesn't have much to contribute to end-to-end testing other than just to provide the connection. So what we're actually going to talk about in more detail is RF testing. The reason you do RF testing is to check against marginal devices, because you have devices that may pass simple end-to-end testing, but if they get out in the real world, they'll perform badly because they have maybe problems with connectors or cables or bad solder joints or things like that. That after a few thermal cycles or in some kind of marginal coverage conditions, you'll notice that they perform badly. So what we're going to talk about here is actually RF testing, and there are two types: uplink, which is the communication link from the device under test to the LabKit, and there we're worried about what we call path loss and SNR, signal to noise ratio, and downlink, which is from the LabKit to the device under test. And what's happening in downlink measurements is that the device under test is reporting back to the network how it sees the signal coming, how it sees the network signal on the downlink. So downlink testing is actually based on measurements received back from the device under test. So switch over to the SSH interface. And we lost the IP connection to the LabKit, so I have to log back in. Sorry again. Okay, so we have a device connected right now, and because of the screen resolution, this line's wrapping around in a way that makes it a little hard to read, but we'll walk through it real quick. We have here path loss of 36 decibels, and we know from the configuration of the test fixture. Let me go back to the whiteboard just a minute, and we'll talk for a minute about what this path loss really means. Excuse me. So in our test fixture, Here's our test fixture again. We have 30 dB attenuator on each side. We have a splitter, another splitter. We're losing 3 dB in each splitter. So the expected loss through our test fixture is 36 dB. We expect to lose 36 decibels through this test fixture by design. And if we go back and look at the reported path loss in this connection right now, we see that it is 36. And what that tells us is that this connection is working just fine. This particular device under test is reporting exactly the path loss that we would expect it to report. And if that number were significantly larger than 36 in this particular case, that would tell us that, that there's some problem, that there's some problem in the device under test. Maybe a bad solder joint, a bad connection, a bad cable, something like that, or maybe an assembly problem. Similarly, on the downlink, the device under test is reporting back that it sees the signal. It sees the signal from the LabKit at negative 81 dBm. And by taking a reference measurement with a known good device, we know that this is normal. That the reporting that the way the LabKit is configured right now and the test fixture that we're using, that we would actually expect the device under test to report back an RSRP of somewhere around negative 80. So we know that this connection is okay. And that's basically what it comes down to, is just looking at these power levels. And if they differ from what you expect in your test fixture, if they differ from what you see from a known good reference device in the same test fixture, you know you have a problem. You know you're dealing with a marginal device that needs to be pulled off the line and figure out what happened to it. So let's switch the video back. It's a fairly simple test, but it's very effective. And so, okay, so what we wanted to show is how to get how you would get these measurements, these physical layer measurements. How would you get access to them in an automated system as part of a production line test system, as part of your test control system? So, and we do it by retrieving those measurements from what we call the measurement engine, which is inside the eNodeB and tracks events and quantities of different types. And it's pretty simple. It just does a search based on regular expression. So if I want to find RSRP, I can say, ENB measurements pattern equals RSRP, and I get the RSRP, average RSRP. I can also get average RSRQ. These measurements are available globally for the entire eNodeB. They're also available on a per UE basis, but in most of these test fixtures, you're only going to be running one device at a time. So just looking at the global number is fine, and it's a little easier to do. Other measurements that are of interest that you would look at, again, let's trim that down a little bit. So average path loss is 38 decibels, and this is averaged over time. And if you look at the differences, if you look at the times here, it actually tells you in the Unix epoch when the time the report was generated and the time that the report started. So this reported path loss average, for example, is a number this is the average over the period between these two Unix times. Some other ones that are also interesting. There's something called power headroom, which is here. Power headroom is a report from the device under test of how many decibels, how many more decibels of power the device under test is capable of sending. So when we see this number right now, it says power headroom average 42 decibels. What that means is that on average, this device, this Huawei Flybox, is doing its uplink transmissions about 42 decibels below its full power level, which means it's very, very low transmission power compared to what it's capable of. If this power headroom number were closer to 0, that would tell you that the unit is being pushed, that the transmit power in the unit is being pushed close to the limit of the amplifiers. If that number hits 0 or becomes negative, that tells you that the device under test is transmitting at its maximum power. And you can use this power headroom number if you need to make a maximum power test. You can use the power headroom number to verify that you actually are at maximum power. Sometimes the power headroom number will show up as negative. That doesn't mean the device is actually transmitting more power than it's capable of. What that means is that the eNodeB has asked the device to do something that would have caused it to require more power than it's actually capable of. The true maximum transmitted power can't exceed 0 decibel headroom, but if it reports negative headroom, what that means is the eNodeB is asking the device under test to do things. Oh, boom, we're back. Okay. So again, because we're having network problems, I hope you caught all that. And this is again described if you go to the link, the RF testing link on this slide. It's a link to some documentation in our public wiki about some of the measurements that are available and how you would get them. Again, back to the device. The eNB measurement engine it's all sorts of information in here, but again, the ones you'd be most interested in are path loss, power headroom, and RSRP, because these actually tell you a lot about the amount of loss, the amount of attenuation between the device under test and the LabKit itself. And if these numbers match the numbers that you get with the known good reference device, then the device under test is okay. And if these numbers don't match what you get with the known good reference device, then the device under test is not okay. And it's really pretty simple. While we're here, I'll also give you another quick thing of what we call the overall performance report. So what you see on the screen right now is the overall performance report of the eNodeB averaged over the time of this seminar since we started running. And it basically says that the eNodeB has been averaging about, it's been averaging about 14 kilobits per second, and that's mostly because it's idle. It's not really doing anything. But the performance report like this gives you a real quick overview of how the system is behaving, in terms of throughput. And the numbers that are used to compute this throughput are also available from the measurement engine, and they're documented. So if you want to extract this information, and do these types of calculations in your test control system, all this information is available through the measurement engine. All this report was generated from the information in the measurement engine. So we're going to call Rob because we lost Rob with all the network stuff. Pardon me just a moment. Hello.
Hey, can you guys hear me?
Yeah, if you turn the gain down on the mic just a bit.
How about this?
Okay.
Hey everyone, so this is Rob from Milan. I just wanted to get everyone's attention. Although the recommended method and solution might be a bit costly, so the more cost-effective way of testing a device is with a little enclosure that you see here, which is basically a enclosure that can fit several phones and not much more than that. So then the question question is basically how do you connect the device? So I'll get into that a little bit later. But another important point that I want to bring up is that even though the cage is supposed to protect the outside world from harmful transmissions, the devices under test are also benefiting greatly from being inside of the RF enclosure because all of a sudden you have a very controlled environment for them. So there's no random devices that jump onto your test network. There's no random towers that the phones will try jumping over to. So you can very greatly control everything that happens, and those phones do, and the LTE LabKit does. So definitely look into RF test chambers, specifically Ramsey cages, because they work very well and they are pretty cost effective. So on the next slide, basically one way of connecting the LTE LabKit in a conductive way is to remove the antennas on the back of the LTE LabKit and using a combiner, basically combine both ports into a single port that you can then feed in through the side of the test chamber. So here on the left side, for example, there's a couple of SMA cables that allow for a signal to go from the outside world to the enclosure. So essentially when you ports on the back of the LTE along with a 30 dB attenuator to ensure that the DUT is not saturated, you can then have a SMA port on the inside of the enclosure that can then have a sort of SMA to UFL pigtail connected directly into the mobile handset's antenna port. So an alternate solution is to use a two-way combiner to connect the two RX and TX ports on the outside of the enclosure, and then hook up a antenna of the enclosure. So this antenna will basically emanate radio waves inside of the enclosure, but they won't propagate outside. However, antennas should be used with caution. And David, I'll pass this back to you.
Okay, Rob, thanks.
Yep.
Yeah, also, if in the test set that we have, in the test set that we're using right now, I'll go back to the drawing on the whiteboard, that it's important in these test fixtures, if you're using a combiner, if you look in this particular case, I'll draw it bigger so that you can see better. I apologize. So we have the transmit and receive ports on the LabKit. And we have a splitter combiner. And in the case that Rob's talking about, this goes to an antenna port inside an enclosure. It's important that you have attenuation here on the receive and transmit before they get to the splitter. And the reason for that is because if you just take the TX and the RX and send them straight into a splitter like this, a lot of times the splitter may not have enough isolation. And what ends up happening is that the transmit power leaks back into the receiver and desenses the receiver. You're basically jamming yourself. So there's two solutions to this. Well, there are three solutions to this. One is just to use attenuation on this side of the splitter. That's option one. Just, use plenty of attenuation. Option two is to use a high isolation splitter. And by high isolation splitter, we mean, at least 20 decibels of isolation, maybe more. Option number three is to use a device called a circulator. which will also give you at least 20 decibels of isolation. The thing about circulators is that they're made for specific bands, and so they're band specific, and they're also fairly expensive. Hundreds of dollars versus less than $100 for these solutions. And there's actually a fourth solution, which is to use a duplexer. And again, duplexers are band specific. These two solutions are not band specific. They can be used over huge bandwidths for almost any. You can build a test fixture that'll work for almost any LTE band. I see we just lost the feed again. These two solutions are very wideband solutions with attenuators or high and high isolation splitters. You can build a test fixture that'll work for just about any LTE band. These solutions are not so flexible. They're all wideband circulators that might work for a wide range of bands, but not for all of them. And duplexers are most definitely band specific. So when you're working, especially when you're working in FDD bands, this question of self-interference and self-jamming is an important. Way back. Okay. So I was just again to the question of isolation. We find that about 20% of our customer support calls are ultimately related to issues of how the device under test is being connected to the LabKit. Is it an over-the-air connection? If it is, we have problems with noise and interference and interference from the cellular networks, interference from other noise sources in the environment. And in wired connections, we often have problems related to self-interference or simply too much power. And I don't mean to harp on this issue a lot, but lost connection again. I don't mean to harp on this issue a lot, but the fact is that these devices, without proper isolation, proper connection, can produce enough power to damage each other. So you can permanently damage a LabKit with the power that in a direct connection to an IoT device. Lost the connection again. So I'm glad y'all could join us for this. I'm glad everyone could join us for this. I apologize for the problems we've been having with the network connections. This is our first time doing a webinar, and I think we learned a lot. And have a lot better experience next time. So I apologize for the connection problems. I realize that was tedious. But thank you very much for joining us. If you want more information, you can go to YateBTS.com or contact us at sales.ss7ware.com. Also, before we go too much further, this slide was slightly out of order. These are sources you might find for some of the components that we've talked about for connecting your IoT device. And we'll come in right now and we'll answer some questions. Before we close this up, we'll take some questions and answer them. Okay, so one of the questions we just got here, is there a way to force the UE into a max transmit power mode and hold it reliably in an OTA configuration? In OTA, maybe not. And the reason for that is because if you're in an OTA connection, you don't really have any control over the attenuation of the system. And if the eNodeB tries to hold the device at max power, it looks like the connection just froze again. Okay, I'm still connected. So if the eNodeB tries to hold the device at max power, what's going to happen you can end up saturating the receiver of the eNodeB itself. So there's actually in an OTA connection, generally speaking, you don't have a very direct way to hold the phone at maximum power, just because the eNodeB has to hold the phone at a power level that actually allows it to be able to still maintain the connection and control the phone. And if we drive the phone up to maximum power and there's not enough attenuation, what ends up happening is that the device under test will saturate the receiver of the eNodeB, and then you lose the connection because you just can't receive under saturated conditions. So it's much better to, if you want to do maximum power testing, the much better way to do that is to use a conducted test fixture, with attenuators, and put sufficient attenuation in there that you can put sufficient attenuation in there that you can drive up the power level on the UE without saturating the eNodeB. All that said, actually I recognize the person asking this question. They're a customer, and we've had this discussion in customer support. We can come in and we can come in and actually we can come in and give you a hook to let you drive power headroom to zero. We do this sometimes for customers where we can put in a hook to allow them to do this in configuration and just drive your power headroom to zero. But in an over-the-air connection, that might result in some pretty flaky behavior. Okay. Any other questions? Okay. I apologize again. We didn't really get to cover some of the things I wanted to cover because we've been having these consistent network connections, and we've run over time. We'll put the slides. We'll attach the slide on this YouTube channel, and people can come in and look at them. But I'm really glad people joined us. I hope you got something useful from this, despite the technical problems we had with the presentation. And in our future presentations, we'll run things a lot more smoothly. So that's it. And again, thank you everybody for your time. And I hope you got something good from this. Good night.